Today we're talking about solving compound inequalities. A compound inequality is an inequality formed by two different inequalities and joining them with the words and or the word or. Okay, so the graph of a compound inequality with the and, this one is the intersection. Just notice this right here. It's the intersection of the graphs of the inequalities. The graph shows the numbers that are solutions to both inequalities. So looking at the two examples we have here. So we have x is greater than or equal to 2. And that's what the graph would look like. It would start with a closed circle and go on forever to the right. We also have this one where it's less than, which means an open circle at 5, and less than means goes this way. So if I was to write a compound inequality like this one, now notice the word and is actually written there, which sometimes you will see, and also notice this one. So when I see something that looks just like this means the word and. So if I just saw this piece right down here, I would know it's an and statement because of the fact that they are joined together. So notice what happens here is, if I get a compound inequality that's combining both restrictions, I'm going to take these two number lines kind of sitting on top of each other and just follow down to the overlapping parts. So this one little section in here would be the graph or the solutions of the compound inequality 2 is less than or equal to x, which is also less than 5. So because these points up top include this point and this point, that's why it's continued down as a solid. But notice this point, which was the number 5, is included. The open circle means that 5 is not included, so I can't include it down here, and that's why that one's open. So intersection means it's in a solution set for both inequalities separately. So then look at the next one. So then we see the or statements. So for the or statements, what I want to notice here is I have y is less than or equal to the negative 2. I have y is greater than the 1. So then they're both kind of going off in different directions. So in this statement, the or statement means we're okay with either of those working. So basically, like up in here, it's the union of the graph. So we're allowed for either inequality to be acceptable. So we're okay if one is, and we're also okay if the other one is. So these are always written this way. You have this or statement in between, and or means we'll take this whole solution set, or we'll take this whole solution set. So that's why down here we're including both things. Now this kind of looks like they're always going to be going away from each other. That's not always going to be the case, but in the or statement we will take the solutions of one or the other one. The and statements, it has to be a solution set of both for sure. Next, we want to be able to write each word sentence as an inequality and then graph it with the number line. So a number x is greater than negative 8 and, so that's in a keyword there, less than or equal to 4. So the first part, number x is greater than negative 8. And, obviously, is the and part, less than or equal to 4. So let's just write that one separate for the moment. So that would be the two parts. Because we have this and thing in the middle, sometimes you'll see it written like this, but we also sometimes see it merged together. So the problem with this is I can't just write it left to right, is x is greater than negative 8, x is less than or equal to 4. What we do is the following. So we would actually put the x right in the middle. And so what we would do is we would focus on the least side first. So negative 8 on the number line is a much smaller number than the 4. So once we recognize the negative 8 and the 4, we kind of put them in the order like as if they were on a number line. And now I look at my two symbols. So this one reads perfectly left to right like we normally would. X is less than or equal to 4. So I can put that one in its place. The first one, though, that we did with the negative 8, we can't write it this way because this is saying it's greater than 8, negative 8, but the x is on the left-hand side. So you got to think about this. We've like flipped these two in the opposite directions. So instead of saying it's greater than, we're actually going to have to flip it and reverse the sign to say that it is less than. So these two things are saying the same thing. I just want you to recognize that this one here is probably a more commonly used higher level math one. It's showing an and statement. Okay, so to show that graph, let's kind of do it in two quick ways here. Number one, we would have -8 at the bottom and then +4 on the other one. So I'm just going to draw two number lines. Okay, so if I was to make my number lines -8, we're going to go by 4s just so you can see this happen. The first one, if I look at x is greater than -8, we would have the open circle at -8, and it would go this way to the right, which is the greater than sign. It would look like that. The second one would start at 4, but it's a closed-in circle because of the or equal to, and it's going left because it's less than from that point. So remember, the and statement takes the overlapping part. So the overlapping part would start here at 8 and go up to 4, and then this one was going to stop because the 4 doesn't go beyond it to the right. And to the left, this one's going to stop at -8 because it doesn't go further to the left. So our final answer would look like this. We would then just say our final solution would be an open circle at -8, a closed circle at 4, and this segment in between that covers the distance between those two. So here is the number line graph and the above solution to this one. On the second example, we have y is at most 0 or at least 2. So as two separate parts, y at most, meaning it could be 0 or less than. At least, y could be 2 or greater than. Could be higher than 2 or less than 2 or equal to 2. And this good old or statement means we'll take them both. Okay? So this is this way this one is written. This one doesn't get written differently. We don't combine them together. So the written answer would look like this. You would have each inequality separate with the word or in between them. In this case, as we're drawing our number line, we would have, I'm going to put 0 down the middle. We have a -2 and a 2. So we have the 0 for the first one. It's closed in circle because of the equal to part, and it is going off to the left. In this case, we have the second one going at 2, and it's closed, going off to the right. And notice you can see all my arrows, and you can tell which one's bold versus just a number line. So because the or statement, they do not have to overlap, and that would be the answer to the second one. Now we might get to some more complicated ones where we have to solve for the compound inequality with the and statement. So remember, with the and statement, we don't see the word or. This tells me it's an and without anybody telling me that it is, right? We can see that it's connected on both ends. Those two inequality symbols say that it is two inequalities together, and is how they are kind of working together. So here's how we have to solve this. So we solve it just like we would solve this as a normal equation in a sense. So we see this middle expression, x minus 2. So we need to get x by itself. So we're just going to do what we typically do. So I'm going to use the inverse of the -2, and I'm going to add 2. And notice this time there's actually 3 segments that I'm adding to 2. And then I just keep following down my steps. So -4 and 2 is -2. I get x, and I get 5. Now x is all by itself. It's an and statement, so that means when I draw my number line, I have to consider the two things. It's already in the correct order because -2 is smaller than 5, so it belongs on the left-hand side of my inequality, or else I'd have to move that around. But basically what I have here is, I'm going to go -2, 0, 2, 4, and 6. I have an open circle at 5. I have an open circle at -2. And again, remember, I'm reading this one as x is less than 5, and this one as x is greater than -2, even though it looks like a less than sign. We're kind of reading it backwards. So then the overlapping part, greater than -2, would be heading this direction. The less than 5 would be heading in this direction, so the overlapping parts would stop at the -2 and at the 5, and that would be the solution to that one. On the next one, so again, I'm going to focus on that middle expression. I would be subtracting 1 from both sides, actually all three sides, and I'm going to get -4 is less than -2x is less than or equal to 8. Then the next step, and this is where we have to be careful, I'm dividing by a -2. Now remember, when we divide by a negative number, or if we multiply by a negative number, I'm going to do what I see for the operations. So I'm going to get 2, I'm going to get x, and I'm going to get -4. But also remember, the symbols have to reverse. So now it's greater than. Now it's greater than or equal to. And then also what we want to do is we want to make sure that we reverse this again, because I want this -4 to be on the left. Notice here that this symbol is saying greater than -4, but now I'm going to be putting it here and working backwards, so I got to keep that in mind. So the x is now going this way, and then again the symbol that 2 is greater than x is going to have to reverse at the same time as I reverse it again. So then when I do my number line, this time I have 0 to -2, -4. I have the closed circle at -4 going to the greater than side, and an open circle at 2 going to the less than side to get that as my solution here. So this would be the best answer for our compound inequality as well as the graph. This is the best answer over here, and here is the graph. So next we have a compound inequality that we're solving for with the OR statement. Now notice these two are separate already. So you just do these like we did in 2.4, we're just solving multi-step inequalities. So for this one, I would be adding 5 to get 3y is less than -3. Divide by 3. Y is less than -1. And then I move on to the second one. So I'm adding 1 to both sides. 2y is greater than 6. Divide by 2. Y is greater than 3. And again, because of this statement, we have an OR statement. So this is my final answer as far as writing the inequality. And then to show the graph of this on our number line, we want to have -1, 0, 1, 2, 3. Try to keep them as best spaced out as you can. We are less than, so it's open circle going off to the left, less than the -1. And the other one is at the 3, it's also open going off to the right. And again, the OR statement means we will take either of those solution sets, so both of those are fine. We haven't really talked about this much, but if you are not sure if you have an answer correct or not, you can always try something like this and say, well, I'm going to pick something in my bold area or not my bold area to help me as a semi-check. So for example, the number 0. The number 0 should not work for this inequality because it's not part of our solution set because it's not bold. So if I plugged in 0 here, I would have 3 times 0 is 0, minus 5 is -5. Is -5 less than -8? No. But because it's an OR statement, it has to work for one or the other one, or it's not part of our set. If I was to plug in a 0 here, 2 times 0 is 0, minus 1 is -1. Is that greater than 5? And the answer is no. So that is correct, at least on the 0, because it didn't work for this one, and it didn't work for this one. So you can use that as an idea on how to test your solutions. This last one we're not going to spend much time on, so I'm really not going to spend a whole lot of time on this. We're trying to write and solve the compound inequality that represents the possible operating temperatures in Fahrenheit. And I think that's where this is somewhat of a problem to work on. We're not going to really stress about this a whole lot. But just so you know, not something that I would expect you to know, to convert from Fahrenheit or Celsius to Fahrenheit, you would use this formula. So if I take 1.8 and multiply it by the temperature in Fahrenheit and Celsius, and then add 32, that tells me what the temperature in Fahrenheit is. So the 0 degrees Celsius, if I was to plug in 0 times 1.8, I get 0, plus 32 is 32 degrees Fahrenheit. If I'm looking for 35 degrees Celsius, when I plug it into the calculator, multiply it by 1.8, and then add 32, that's the equivalent to 95 degrees Fahrenheit. So if you look at the picture here, it's saying that the operating temperature needs to be this in Celsius. What we're going to do is write an inequality that explains the same idea of that range that it can have in Fahrenheit. So all you'd really be doing is you'd say it has to be less than or equal to 95 degrees and greater than or equal to 32 degrees to be the Fahrenheit range of the 0 to 35. So describe one situation in the surrounding temperature could be below the operating range and one that it could be above. Well, obviously we know one situation when it's below that operating range is if somehow you dropped your phone out in the snow someplace. Obviously it would be below 0 or 32 degrees Fahrenheit, and that will become obviously too much danger for the phone to be able to react. On the same idea of that, we all know on a hot sunny day, if you left it out on the pool deck someplace or on a boat someplace in the direct sunlight, it's going to definitely climb above the 95. So hopefully this helps. We'll talk a little bit more about compound inequalities when I see you this week. If you have any questions, feel free to ask, and we will see you then.